This video is gravity, the way things fall, acceleration, dropping cannonballs on different planets. When you drop something, how does it fall? Initially, it is not moving, but it begins to move. Its speed increases as it falls. It accelerates downward. Let's get a feel for this gravitational acceleration by watching a demo of objects falling. Let's drop some cannonballs off the famous Leaning Tower of Pisa. Let's drop one cannonball every second from a height of 50 meters, about 164 feet. Gravitational acceleration at the Earth's surface is about 9.8 meters per second squared. This means that the speed will increase by 9.8 meters per second for every second of fall, constant acceleration. We can ignore the effect of air resistance. We're dropping cannonballs, not feathers. While the cannonball is still falling, t seconds after we release it, its instantaneous speed will be 9.8 times t meters per second. Under constant acceleration, its speed increased linearly from 0 at rest to this value. So its average speed will have been half as much as the instantaneous speed, or 9.8 divided by 2 equals 4.9 times t meters per second. It has fallen for t seconds at average speed 4.9 times t meters per second, so the distance it has fallen is the product of those two values, or 4.9 times t squared meters. Each cannonball will hit the ground 3.2 seconds after we release it. 4.9 times 3.2 squared equals 50 meters. 3 other cannonballs will still be falling as we release each new cannonball every second. Before it hits the ground, its instantaneous speed is 9.8 meters per second squared times 3.2 seconds equals 31 meters per second. Pretty fast. Luckily, our simulation doesn't get tired and doesn't run out of cannonballs. Notice that the distance between two falling cannonballs increases over time until one hits the ground. This is because the ball we released first has been falling longer and has acquired more speed than the one we dropped second, acceleration. Okay, good, but what about gravity on other planets? Surface gravity is approximately proportional to a planet's density times its radius. Mars's density is about 71% of Earth's, and its radius is about 53% of Earth's. Mars's surface gravity is about 3.7 meters per second squared, or 0.38 times Earth's surface gravity. We would weigh 30% what we weigh on Earth, ignoring the heavy spacesuit we would have to wear. A cannonball dropped from 50 meters above Mars's surface falls more slowly than on Earth. Can you see that the cannonball falls more slowly on Mars than on Earth? T seconds after we release a cannonball, it will have fallen 3.7 over 2 times t squared meters on Mars. Each cannonball will hit the ground 5.2 seconds after we release it versus 3.2 seconds for Earth. 5 other cannonballs will still be falling as we release each new cannonball every second. Before it hits the ground, its speed is 3.7 meters per second squared times 5.2 seconds equals 19 meters per second versus 31 meters per second for Earth. Can you see that the speed hitting the Earth is faster than for Mars? The distance between successive cannonballs increases faster on Earth than on Mars. Can you see that in the demo? Good. Now, what about Jupiter? Gas giant Jupiter's density is about 24% of Earth's, and its radius is about 11.2 times Earth's. Jupiter's surface gravity is about 25 meters per second squared, or 2.5 times Earth's surface gravity. A cannonball dropped from 50 meters higher than Jupiter's surface, its top cloud layer, falls faster than on Earth. Each cannonball will hit the surface, the top cloud layer, 2.0 seconds after we release it versus 3.2 seconds for Earth. Before it hits the ground, its speed is 25 meters per second squared times 2.0 seconds equals 50 meters per second versus 31 meters per second for Earth. Can you see that the gravitational acceleration and the speed hitting the ground are higher on Jupiter and less on Mars? Great. Now what about the Sun and the Moon? The Sun's density is about 26% of Earth's, and its radius is about 109 times Earth's. The surface gravity of the Sun is 274 meters per second squared, or 28 times the Earth's. Our simplified virtual cannonball falls 50 meters in 0.6 seconds and hits the photosphere at 166 meters per second. The Moon's surface gravity is 1.62 meters per second squared, or 0.17 times Earth's. Our cannonball falls 50 meters in 7.9 seconds and hits the surface at 13 meters per second. Pluto's surface gravity is 0.66 meters per second squared, or 0.067 times Earth's. Our cannonball falls 50 meters in 12 seconds and hits the surface at 8.1 meters per second. The dwarf planet asteroid Ceres' surface gravity is 0.27 meters per second squared, or 0.028 times Earth's. Our cannonball falls 50 meters in 19 seconds and hits the surface at 5.2 meters per second. If we were to fall 50 meters on Ceres, we could probably land pretty safely with a little care. We could jump pretty high there too. Can you see how gravitational acceleration and speed hitting the ground vary from the massive Sun to tiny Ceres? Note that this demo did not indicate the weight or mass of the cannonballs. In the 4th century BC, Aristotle taught that an object falls in proportion to its weight. The heavier a rock, the sooner it will reach the ground. For many centuries, this was accepted as true. It seemed reasonable and logical. But in the 1600s, Galileo thought about this, conducted experiments, and concluded that differing weight does not affect how objects fall when we can ignore the effect of air resisting the motion. Galileo said that a musket ball and a much heavier cannonball dropped from the same height would hit the ground at almost exactly the same time. Let's consider a thought experiment. Let's start by assuming that a heavier ball falls faster than a lighter ball and see where that assumption leads us. Let's attach the two balls together with a strong but thin and light wire. Then we drop the two balls connected by the wire. How fast will they fall? If the heavier ball falls faster than the lighter ball, then the string will let the heavier ball pull the lighter ball to go faster than if they were disconnected, right? Or will the lighter ball slow the heavier ball down? But wait, attaching the two balls together makes the pair heavier than each individually. Will the pair fall faster than the heavy ball did when disconnected? This is pretty confusing. What if our assumption was wrong? If the heavier and lighter balls fall at the same rate, then they would continue to fall at that rate if they were connected by a strong, thin wire, and we would have no contradiction. That seems to make sense. Falling due to gravity is independent of the mass of the falling object when we can ignore the effect of air resisting the motion. Some science museums demonstrate a heavy ball and a feather falling at the same rate in a glass column or plastic column where the air has been evacuated. When the Apollo astronauts went to the moon, one of the astronauts dropped a feather and a heavy ball on the moon, and they fell at the same rate because the moon's atmosphere is almost non-existent. This demo was simplified ignoring air resistance and viscosity. The demo also ignored that Jupiter and the Sun don't have a solid surface and ignored the Sun's radiation and solar wind. I hope you enjoyed this demo and that it was useful and interesting to you.